All right, so folks that are just joining us, I had a chance to look over the discussion number 9. It seemed like there were 3 main camps of questions, and so that's where we're going to focus on today. And the first one was in the superposition approach, where we are sort of guessing solution forms. Folks wanted to know in particular, like, why do we multiply sometimes? So that was one sort of clump of questions. The second one was around the Wronskian and maybe realizing that that was not as straightforward. So taking a look at the formula for that one and how to apply it.
Is there a video for the Wronskian?
There is not. I have had quite the week, and my apologies. You know, when you think you're going to sort of have more time and then it turns out that you don't have more time and then you keep putting things off, but that is very much on my list of things to do before the exam, to be clear, before the exam. All right, and the third camp was with the spring mass systems. I think folks were sort of a little confused about how to set those up. And I heard some really good feedback about looking more at the setup and focusing on that piece. So let's kind of get started with the superposition one, and then we'll go from there and see what sort of organically comes up in our conversation. But I think in particular, folks were looking at questions 5 and 6 on the homework and wondering why we had to multiply by x. And so what I'm going to do is I'm going to write down some of the y sub c and y sub p's from the other homework questions, and I think we can draw a pattern from that, okay? So I know I said in the video there's something about duplicates, but I think maybe that was a little bit vague, so I'll try and clear that up here. All right, so when we're looking at the solutions, if we look at like from homework 4, okay. So from homework 4, for question 1, we had a y sub c that was like c1 e to the negative 4x plus c2 e to the negative x. And we had y sub p equals a. For number 2, we had y sub c equals c1 e to the negative 2x plus c2x e to the negative 2x. And our y sub p was a quadratic guess. And then if we sort of take a look at number 3 was very similar in form. The numbers were different, but the forms were very similar. And then in number 4, we got y sub c equals c1 cosine of root 2x plus c2 sine of root 2x. And our y sub p was a quadratic situation multiplied with an exponential. Okay. And so let's pause here for a moment. So I'm not just continuing to write letters on a board. But in particular, if we look at our y sub c's and we compare them to our y sub p's, we'll notice that like in the first one, this is our y sub c. It has like exponentials. But if we look at the y sub p, it's just a constant. right? So there's no part of the yellow one that shows up in the green one, right? And same thing if we look at number 2, we have this quadratic one, but the y sub c is again an exponential with the repeated roots, right? And so there's nothing in the green one that is also in the yellow one. And as sort of a last example of that, here I have sines and cosines. But if I look at my y sub p, I don't have sines or cosines. I actually have a quadratic and an exponential, okay? So for the first 4 problems, when you worked on those, you could kind of cruise and say, all right, I'm just gonna follow the process that we did in class. And you were able to obtain a solution. But if we look at the questions from example 5 and 6, 5 has c1 cosine 2x plus c2 sine 2x as the y sub c. And the y sub p, if we guessed it, would have been like an a cosine 2x plus b sine 2x, right? And if we also, just to gather a little bit more information, took a look at y sub c from number 6, we get c sub 1 e to the negative 2x plus c sub 2, and the y sub p was ax plus b plus c e to the negative 2x. And so if we look at these two, 5 and 6, a little bit more carefully, we might see that the y sub p has some part, if not all, of the y sub c in it. And so specifically, like we see a cosine 2x and a sine 2x in the y sub c, but we also see a cosine 2x and a sine 2x in the y sub p. And that created problems for us. When we tried to go and simplify it, like follow the method, we realized that it just wasn't working out. We were getting some very weird situations. And similarly, in here, it wasn't that both of them showed up, but this e to the negative 2x showed up in both my y sub c and my y sub p, okay? So the way that we handle the situation in the blue is by multiplying, okay? So if there's a duplicate term or the same term in your y sub c and your y sub p, then you want to multiply by, you're going to start with x, but you could multiply by any x to any power to get rid of the problems that cause this duplication, okay? Meaning that for number 5, our guess was y sub p, but once we went down that rabbit hole, it didn't work out. So we should try multiplying by the lowest power of c of x. So just x. Multiply by that lowest power and see if it's enough. Okay. If this works, then you're good to go. And how do you know it's going to work? Because you don't want to go through a whole problem and then realize that it doesn't work. You want to multiply by the smallest thing that's going to make this cosine 2x different than the other cosine 2x. And so as soon as I multiply by an x, I'm creating a different term, right? Because now it's x cosine 2x, not just cosine 2x. And now it's x sine 2x, not just sine 2x, okay? And similarly, if we look at number 6, this was not the y sub p that you should have used. If you tried this one, you also ran into some problems. And the problems are caused because this e to the negative 2x is duplicated in your y sub c. And so since it's just e to the 2x, let's go ahead and try multiplying everything, multiplying that term by the x, right? So we've got ax squared, because now I multiply that one, plus bx plus Now it's cx e to the negative 2x, and it no longer matches what's in the y sub c. All right. So does that make a little bit more sense about why we multiply through? All right. So if we were to summarize this, um, I wonder if you could maybe share out in the chat, like what would be a good way to summarize this? So like as we're heading into the exam on Monday, how would you summarize this for yourself so that you'll remember when to look to multiply by an x and when you wouldn't need to? All right, so in other words, when we're solving differential equations using the superposition approach, how would we know when we can just pull straight from the table and when we would need to do something differently? Yeah, all right. Yeah, so when solving differential equations using the superposition approach, we could say use the table to guess solution forms. Maybe a however, right? However, let's see, if the guess for y sub p matches any part of y sub c, then multiply by x um, to eliminate sort of weird answers unattainable answers. Okay, so when you're solving for the differential equations using the superposition approach, if we look back over the first 5 homework questions, we can see that the first 4, the y sub c and the y sub p did not share any terms, so we didn't have to do anything. However, in examples 5 and 6, they did share some terms, right? 5 shared all the terms, 6 shared only one of the terms, but in both cases, we had to multiply by x to eliminate any weird or unattainable answers, okay? All right, so I hope that answers that first question. The second sort of group of questions was around the Wronskian. And so I just wanted to ask you folks a little bit of a clarifying question. Was it just that the notes itself were hard to follow, or that you weren't sure sort of about the process or the formula, if that makes sense? So I'm going to pull up my 4.6 notes right now so I can kind of see those on the side. But if you have a specific direction about like what makes the Wronskian method hard, I would love to hear a little bit more about that.
The Ronskin was really difficult because a matter of like really detailed memorization and like doing everything to the T. And if you mess up one thing, then the rest is hard.
Yeah. All right. Would it be beneficial to maybe walk through one of the homework questions from homework 4 that uses the Wronskian?
Yeah, I think that would be really good just to
Okay,
see.
cool, cool. All right, so it looks like I use the Wronskian for 7, 8, and 9 uh, on the homework. Is there one of those that sort of stands out that you would be beneficial to go over? So I know I asked that like you have all of your homework pulled up all the time right away, but that's okay. All right.
I think number 8.
Okay, cool, cool. So that was, so we'll say number 8 from homework 4. And that was solve y double prime minus 9y equals 9x over. Oh yeah, when I was typing the solution to this one, I was like, oh, it's so long. All right. So if we follow sort of the methods from the notes, all right, then we would start by finding that y sub c, right? And so we're looking primarily at that first side. And so we could say m squared minus 9 equals 0. So m equals plus or minus 3, right? If we solve for m. And so that means that our y sub c equals c1 e to the negative 3x plus c2 e to the positive 3x. There's no rhyme or reason. I think I tend to put the one with the negative or the smaller exponent first and then the bigger one, but it doesn't really matter. Okay, so if that was maybe a question that you had, it doesn't really matter. And then we dove into the meat of the work, right? Finding y sub p. And if we were to sort of summarize this into 2 steps, we had like an A where we had defined the Wronskian, and then a B where we had to find, like use that big formula, okay? Now, we are remote. This is an open resources from this class kind of exam. So, but even outside of that, I wouldn't expect you to memorize this particular formula because it's just so long and gross. But let's go ahead and find that Wronskian. So the Wronskian, these come from the solution that you have, like the terms that you have in your y sub c, okay? And so again, it doesn't really matter the order in which this happens, but you're gonna grab one of your terms from your y sub c, and you grab it without the constant because we don't know what that constant is yet, and we're more focused on like the structure. And so the structure really comes from e to the negative 3x. And then the other one we want to grab is the e to the positive 3x. And we're just going to write those here, e to the negative 3x, e to the positive 3x, okay? So this goes with that term from your y sub c, and this one comes from the other term in your y sub c. The second line is just the derivative of the first line. So if I think about the derivative of e to the negative 3x, I'm going to get negative 3e to the negative 3x. And if I take the derivative of e to the 3x, like the one in the red, I'll just get 3e to the 3x. Now, the Wronskian is defined as basically taking the product here and here, and then we are subtracting the other product. That should be a structure that is familiar from linear algebra, all right? But I know I didn't necessarily write out all of the multiplication steps. So let's take our, we have 3e to the 3x times e to the negative 3x equal, minus negative 3e to the negative 3x times e to the 3x. And so we just want to be really thoughtful about our exponent rules, right? And so when we think back to like what we know about exponents, if I have the same base, then I'm just going to be adding those exponents. And so in this case, those exponents ended up being the same, like adding to 0. So that's why I got 3e to the 0 for that first term. I went ahead and clumped the two minus signs together as a plus. And then I got 3 again, and then negative 3x plus 3x gave me another e to the 0. E to the 0, one of our lovely numbers, e to the 0 goes to 1, and so our Wronskian is really 3 plus 3, or 6. Okay. So I don't think this is where the problems ensued. I think it was really in the second step, but I do want to give a little bit of time here in case there were any clarifying questions about finding the Wronskian here.
And so if your y sub c was e to the 3x plus the c2 e to the negative 3x, so like if you switch the roots, your Wronskian would be negative. Would it be negative?
Let's see. Yes, and I think that will flush itself out as you go along.
Okay, thank you.
Okay. All right, so once you find your Wronskian, then we're going to go ahead and actually find our y sub p using the formula. Okay. And so we will take the time to write out the formula and make sure that we're plugging things in the appropriate places. Okay. So the formula says that y sub p is going to be equal to negative y sub 1, the integral of y sub 2 g of x all over the Wronskian, plus y sub 2, the integral of y sub 1 g of x over the Wronskian. Okay. Now, what are the y1s and the y2s? Those are our yellow and orange color-coded situations from above. Okay, so y1, and it might even be helpful if you're worried about plugging things in the wrong place to make like a little running list of what you're going to plug in where. So for me, I said that my y sub 1 is e to the negative 3x, and my y sub 2 was the e to the 3x. Okay. I said that my g of x is going to be whatever's on the other side that makes it non-homogeneous. So 9x over e to the 4x. Oh, that's a 3x. I'm sorry. Right. So our g of x is simply from the other side. So 9x over e to the 3x. And our Wronskian is 6. Now notice if you chose your y1 and your y2 differently, like you swapped these, that would give you a different sign for your Wronskian, but you're also plugging in things in opposite places in the formula. So all of that should take care of the fact that you got a different sign along the way. All right, so I've seen some folks in class really like enjoying the color coding situation, and that's fine. So whatever strategy might work best for you. This is the one piece that I like handwriting my solutions, but it's like a lot to handwrite. And I like the LaTeX because I think I can, and it like I can sort of write what's happening better, like I can narrate the process better. But I almost wish I could do a blend of both, right? So we can sort of plug all those Wronskians down there. And then last but not least, we have our g of x, which is going to go here and here. Okay. And yes, I think this is the most algebraically challenging process that we've met. As someone said earlier, one step goes wrong and it's like all wrong. So let's take our time with this and let's make sure that we plug in everything where we need it to. So we have y sub p equals negative e to the negative 3x. So negative yellow, integral of e to the 3x times 9x over e to the 3x, all over 6, right? So this is my g, this is my w, this is my y sub 2, and this, without the minus sign, is my y sub 1. Right, so everything matches the colors that I had set forth before, or however you want to notate that, plus y sub 2 is the red one, the integral of the yellow one times the blue one, all over the Wronskian. And so we've got our yellow one right here, our red one on the outside, our blue g of x, and our purple Wronskian. Okay. All right, now it is a be really careful about all of your steps situation. Now, everyone has sort of a different flow on how they like to work through integrals. I think one thing that I really like is I like to see how far I can get algebraically by cleaning things up. And so that means maybe combining some like terms. It means maybe pulling constants out to the front so I don't have to worry about those quite so much. And so what I'm going to do is I'm going to bring the 1/6, like this Wronskian being a 6 means I can pull out a 1/6 to the front. So I have negative e to the negative 3x over 6. Now you can't always take out the Wronskian, but in this case, because it's a constant, you can, okay? And then I'll take the time to write this extra step. I have e to the 3x times 9x over e to the 3x. And if I do the similar thing over here, for the second term, I'll get e to the 3x over 6, integral of e to the negative 3x times 9x over e to the 3x. Now I do want to be really careful, just do a double check, make sure I've got all my signs where I need them to be. And I'll notice that this e to the 3x and that e to the 3x, those reduce. And so my first integral really just becomes the integral of 9x. Okay, let me take the time to write that out. So I'm going to pull the 9 out to the front as well. So negative 9 e to the negative 3x over 6, integral of x dx. Right. Now I talked through a lot of steps here. Let me pause for a moment and just make sure we're okay with how that's simplified there. Just the first term. We'll get to the second term in a little bit. Okay. And so in looking at the second term now, I can again pull that 9 out to the front. So I'm going to have 9 e to the 3x over 6. And I notice here I have an x on the top And then this is e to the negative 3x, but so is this one. So I really end up with x e to the negative 6x because I'm able to add my exponents, right? Negative 3 plus negative 3x gives me negative 6x. All right. So how are we doing so far? We've simplified the first one, we've simplified the second one. Okay. So now that we've simplified these, that first integral is just the integral of x. That should be like, thank goodness, it's just an integral of x. I don't need to worry about much else. But the second one, I might want to make a note, right? So this one is just good old power rule. Even my Calc 1 students who maybe have, limited, much less experience than you folks have with integrals would know how to do that one. This one, though, we're going to need integration by parts. Okay, we're going to need integration by parts for that one. So I'm going to go ahead and set up what I get for the first integral, and then we'll do our integration by parts off to the side. So I know I can reduce here. This is 3, this is 2. So I'm going to get negative 3 halves e to the negative 3x times the integral of x is x squared over 2. Okay. Now I can simplify over here similarly. I get a 3 and I get a 2. I know I have an e to the x on the e to the 3x on the outside. And I'm going to go ahead and open up brackets so that inside of there, I'll be able to put what my setup is from the integration by parts. So if I want to do integration by parts, I need to find a u and I need to find a dv. Okay. I think I said this the first day, we could go to Lipet or Liate. But anytime you have an exponential like e to the something, unless there's a trig function, the e one is not going to be your u, all right? Anytime you see a polynomial, like in this case x, that's going to be your u, okay? That means the rest of it, e to the negative 6x dx, is your dv. You're going to differentiate your u to find your du. You're going to integrate your dv to find your v. Okay, so if you're wondering where that like negative 1/6, like the extra term came from, it's because when you u sub to integrate that, you'll get that extra factor there. And integration by parts, just as a friendly reminder, the integral of u dv equals uv minus the integral of v du. So I'm going to take what I wrote in my setup and I'm going to plug it into the right-hand side of this pink part. And I'm going to go ahead and insert that right here. And so we'll get uv, or negative 1/6 x e to the negative 6x, that's u times v, minus the integral of v times du. Okay. Lots of negative signs. I try and keep track of those along the way. All right. So we've got negative 3 over 4 x squared e to the negative 3x, right? That's what that first term becomes. Plus I have to be really careful here because I already forgot this 3/2 in front of there. So now I'm going to distribute 3/2 to the 3x to the first term. I'm going to have to integrate here before I distribute, okay? So it's sort of up to you whether you want to integrate and then you want to distribute. I think I will do that. So I'm going to keep this -1/6 x e to the -6x plus 1/6. So plus because the minus and the 1/6 I can move out to the front. And the integral of e to the -6x is -1/6 e to the -6x. Okay. So as you can see, u sub takes us pretty far in terms of like, we see u sub a lot, but it's always like the really sneaky cases like this, like e to the -6x or e to the 3x, right? Those are the small cases where we need u sub and sometimes we forget. Okay, so now I think I'm ready to distribute. Minus 3/36 times, nope, I don't want to do that. 3, 1 or 1/24 e to the -3x. Right. Did I miss that term in my answer? I think I did. All right. So when we take a look at what we have so far, all of the terms have the e to the -3x, but we have sort of an x squared, an x, and then like a quote unquote linear situation here. Good question. So when we're thinking about the constants, again, we're sort of wrapping them all up because at the end of the day, we're finding if we're looking for a general solution, we're looking for to keep the C1 and the C2 from the y sub c. But we sort of roll in any constants that might have happened along the way for the y sub p in with those other C1 and C2. So we don't have an extra plus c for the y sub p part. Yeah. Okay. So in looking at my answer key, I think I've got mostly everything except I need to go back and make sure I have this e to the -3x because I'm missing that term in my y sub p. Okay. So if we were to write the whole solution out, just so you know what that should look like, we're going to get our C1 e to the -3x plus C2 e to the 3x plus everything that you found for your y sub p. All right, so this would be a fully correct answer. And again, I think I left out that e to the -3x in the very last term. All right, so yes, for sure, plenty of room for error. I do not plan on giving you something quite so meaty on the exam because as you can tell, this just took us a good chunk of time. So I don't think that that's necessarily, yeah, I don't think that's the best use of your time here. Yeah, so was that clarifying in terms of how to walk through the Wronskian? And would we like to do another question or are we okay?
That was really helpful. I think we
Okay,
can probably spend more time on other subjects
okay,
now.
okay, cool.
Could I ask a quick question about this one and also, well, there's a couple of them actually, but if you would have chosen to not use the Wronskian method here, could you have just changed the 9x e to the over e to the 3x to 9x times e to the negative 3x and then used the superposition approach?
Yes, yes.
And then my other question is for number 7, where it's secant x. Could you have just changed that to 1 over cos x and then also used the superposition approach for that as well?
That's a good question. My gut instinct on that one is no, because reciprocals can get tricky in terms of like, are we taking the reciprocal? Like, if we take the reciprocal of secant, can we just take the reciprocal of the guess? And I'm not sure that that's entirely true, but I also haven't tried that for this particular question.
Okay, thank you.
Yeah. Yeah. And I think that, in this class, we learn a lot of these different methods, and we're thinking about like specific questions, and there might be a particular method that I'm trying to showcase in a question. But as you can tell, there's a lot more freedom in terms of how we approach these questions than there was in, like, let's say a Calc 1 or Calc 2 kind of question, right? A lot of those questions, we sort of have like one way to approach it, maybe two, but like one is clearly better than the other. And I think that becomes a little bit more nebulous when we get into differential equations. So, all right. So let's see, we've taken a look at superposition, we've taken a look at the Wronskian, and then the third clump of feedback was really around spring and mass systems, and in particular looking at the setup of those. Okay. So I know that on the homework assignment that is due on Saturday, that we have about 4 problems that are requiring you to do some setup. And so I wonder if maybe we can sort of try setting up a few of these and see where we get. All right. All right. Has anyone started on the homework yet? And it's totally fine to say no. I'm not saying that to judge anyone. I'm just trying to get a gauge of what might be useful versus what might not be useful. Okay. All right. So we've had some folks who've already tried that.
I'm really just not sure how to do like 2, 3, or 4
Okay,
for the
cool.
setup.
Great. Well, let's go ahead and maybe set those up then. Okay. So if we take a look at 2, so we have a force that is 640 newtons. All right, so now we're looking at the newtons one, so maybe that's a little bit different than what we've seen. So 640 newtons stretches a spring 4 feet. We have a mass of 40 kilograms is attached to the end of the spring. It is released from its equilibrium position. So we might even say that x of 0 equals 0. Right, and so this I got from it is released from equilibrium position. Right. And then it has an upward velocity of 6 meters per second. So that also gives us our other initial condition, x prime of 0. So at the beginning of time, when we start measuring the motion of this mass on the spring, it has an upward velocity, so 6 meters per second. However, we've sort of defined the direction of downwards, the same direction as gravity, to be positive. So upward, even though that's weird for us, upward would be negative. Okay, so initial velocity in the opposite direction from gravity. Okay. So if I were to sort of categorize this question, or not categorize it, but write down the important pieces of information and interpret them, I would maybe get something like this. Okay, so we have this force that stretches the spring. We have a mass that is attached and released from some initial conditions in terms of position and velocity. And our goal is to find a position of motion. So we're looking for our x of t, right? Now, one thing I sort of start to think about as I'm doing these questions is I start to think about what the pieces of information help me find. And so in particular, if we're looking at the force of 640 newtons and it stretches the spring 4 feet, what would we say is that going to help us find?
Spring constant.
Yeah, that's going to help us find the spring constant. Excuse me, and this actually should be meters, right? That makes more sense for newtons and meters. But this force and the distance that it gets stretched, this helps us find our K, all right? So that is a good, helpful thing because we can find our K value. What do the other pieces of information tell us, if anything? Like, what might they help us find? Well, I think these last two, our initial conditions, are going to help us find our C1 and C2, right? So at the end, we're going to have numbers for C1 and C2, but those initial conditions help us find them. So it's nice to have them up front, but we don't really use them again until the end of a problem, okay? All right, so what are our thoughts? How might we want to get started with this? Right, so maybe we take a look back at our notes, see if we need to do some things. And it looks like might not be a bad idea to at least find our K, because even if we don't know where else to go, the fact that we have a force and a distance allows us to find that spring constant. So maybe we should just find that. So we get 640 equals K times 4. And we get K equals 124, 160. Is that right?
What does S represent again?
S represents the distance that something gets stretched.
Hey, Judy, I'm just noticing one thing here, if I could ask a question real quick.
For sure.
In all the other previous problems, it seems like the mass and the force have been the same, but it seems like that's different in this example. But that doesn't matter. Is that's what I'm getting at, I guess.
I see. I see. So it's almost like how do we best explain this? So it's almost like they're giving us two pieces of information, Okay, the force being 640 newtons and stretching a spring 4 meters, that tells us how stretchy the spring is. So it's almost like they're telling us how stretchy the spring is, but not necessarily with the current mass on it. They're just saying, you know, this spring in general has this spring constant, but we want you to find it. So the spring stretchiness is like the stretchiness no matter what weight you put on it, no matter what force you apply to it. The spring constant is inherent to the spring. And so even if they give us information outside of that, they tell us what that spring constant is. We can still use that spring constant in the context of a different problem.
Because K is K for that spring, no matter what force is applied to it.
Exactly, exactly. Okay. So I would agree in the past, we've said, oh, we want to go ahead and find, you know, for this particular system. But in this one, we're saying, well, we just know that here's this spring and it is, you know, we happen to put this other force applied to it and it happens to stretch by this amount. And so now we can say, okay, this spring, no matter what, has a spring constant of 160 newtons per meter. All right. So now we found this spring constant, and that's good. All right. When I read the problem, a few things I notice, like I know I don't have the problem written here, but when I read the problem, I notice that there's not that much information. There's not as much information as, like, let's say, there is an initial velocity that is this, or not initial velocity, but there is a sort of like a beta that is 3 times the initial velocity. Like I don't have that kind of information. And so it's always best to kind of start simple and think, okay, they didn't tell me about any resistance. It doesn't seem like there's a damping situation, right? That damping factor, that beta. So maybe this is just a free, undamped system, right? They're saying in the perfect world, what's going to happen with this spring? So sometimes we're looking for what's there, but sometimes we're also looking for what's not there, okay? And so from our notes, we have that our second order differential equation, dx squared dt squared plus omega squared x equals 0. And we want to remember that omega squared is that we find it from the spring constant and the mass, right? So we have K divided by M. And so when I put things into my equation, my K is 160. My mass, all right, my mass here is, what did I say it was? And the mass is 40 kilograms, okay? So the K and the M, we just plug those in and we get that. And we can clean that up. And from that cleaning up, we might notice that it will be a homogeneous equation. We can use the characteristic equation to find that general form of the solution. And then we can apply the initial conditions that we wrote down to find the values for C1 and C2, okay? So is this what folks meant by the setup, like talking about that front end a little bit more? Or would we like to go further and actually solve that particular problem?
For me personally, I just have trouble identifying what is what and how to find K or beta. So But if anybody has any other ideas and they want to see it, they can say so.
Thank you. All right. Well, it sounds like maybe no, but if anyone changes their mind, we can kind of go back from here. But I did see there was some folks who in that discussion said, oh, we don't really know like what the different solutions are. This, I think, would be a really great way to kind of review the 3 types of solutions that you might have for a characteristic equation. Okay. If you find it hard to be able to sift through all your notes before, like during the exam, while you're trying to answer the questions, it might be nice to just make yourself a little reference sheet of like the important formulas that we've seen, the different types of general solutions, and maybe even just a summary of the process. Like if I was looking at a spring mass, I would say like convert my units, find my K, write and solve my differential equations. But sometimes just that process too helps us like retain that information a little bit more and have it more like ready to go. Okay. All right, well, let's see. That was question number 2 from the homework, all right? But I think question number 3 might be a little bit nicer to take a look at because I think there's more to speak about in terms of the setup for these, okay? So in taking a look at number 3, right? So this is number 3 from the homework. And if I were to read it and then write down some important information, I might say that there is a 1 kilogram mass and it's attached to a spring whose constant is 18. So they're actually telling us the constant here, okay? So instead of giving us like a force and the spring like distance, like how much it moved, they're actually just saying, here's your K value. Don't worry about finding it, but here's your K value, okay? Once we have the K and we have our M, well, I bet we can use that to find our omega squared, right? So if I go back and I were to write this a little bit better, I might say that M is 1 kilogram. And from here, when I have M and I have K, I can find omega squared by taking K and dividing it by M. Right? Now let's read the rest of that first sentence. So, and the entire system is submerged in a liquid that imparts a damping force numerically equal to 18 times that initial velocity. Right? So here's what that tells us. The phrase, a damping constant that is numerically equal to, oops, not 18, 11 times the velocity. Okay, so if you think back to the equation that we saw in class, and maybe I should go ahead and write this down. As soon as we see that idea of a damping constant, the equation that we really want to think about is our d squared x dt squared, and maybe I'll write this version, m dx squared dt squared equals negative kx minus beta dx dt. Okay, this one I think actually might be more useful when you're trying to think about what numbers to plug in. All right, I think the divided out version, I like that idea because it sets us up to be able to solve things. But if you're worried about like not knowing where to plug in what number, then as soon as you list things out, you can start to put them in the appropriate places in the equation. So for example, M is 1. I can go ahead and put a 1 in for this M. K is 18, so I can put 18 in for this K. Now, the phrasing of this damping constant actually helps us remember where it's going to go, because it says a damping constant numerically equal to 11 times the instantaneous velocity. X is position. So dx dt is the velocity. So this damping constant is 11 times that velocity. Okay. And so let's try it this way. Instead of trying to fill it in the way we did in class where we already divided that m away, let's just fill in numbers into this equation. So we have our m, we want to fill that in. We have our k, so we're going to want to fill that in. And we have our beta, and so we're going to fill that in. And so we end up with 1 d squared x dt squared equals negative 18x minus 11 dx dt. Right. Was that a little bit more helpful in terms of trying to figure out like what to put where? If we just plug it right into the non-divided version?
That helps.
Okay. So now we can see that like this spring constant is negative, which means it's going to slow the movement down over time. This damping constant is also going to be slowing the movement down with time, which is why they're both negative. But to a question that was asked previously, once we sort of start to set things up to solve it, I'm going to want to move everything to the other side. Now they're positive, and now I have a homogeneous differential equation of second order. Do we mind if we go further into this problem? Not at all. If it saves you all a little bit of headache this weekend so you can focus on studying, absolutely. All right, so we've got our differential equation. We were lucky in the sense that our m was a 1, so it was almost like the problem was being super kind to us because we didn't have to go ahead and divide by anything, because when we divide by 1, it's going to be the same thing. But what that allows us to do is to go ahead and find the characteristic equation, solve that, and depending on that, we'll figure out what the roots are. All right, so we'll get m squared plus 18.
I have a question. I think it's 11x prime plus 18x instead of
Oh my
18.
gosh, it totally is. You know, in my Calc 1 class, I was trying to factor this morning and I had a sign mistake, and then things were not factoring, and it took me so long to find the mistake. Okay, thank you for that. All right,
You're
so
totally good. You're like talking while doing all of this. It's very appropriate.
well, thank you. It is my job, but thank you. All right, so m squared or r squared plus 11m plus 18 equals 0. This makes much more sense because now we can factor this more nicely, right? So we get m plus 9, m plus 2 equals 0. And then we can find our two roots as m equals negative 9 and negative 2. And again, for no reason in particular, I like to put the smaller root first and the bigger root second, but it doesn't matter whether you write this or if you write it with the C1 and C2 swapped. Okay, that would be either way is totally fine on this. Right? But we know these are real roots. They are distinct roots. And so we just have our C1e to the power plus C2e to the other root. All right. If they were repeated, we would just need an extra t in that other solution. All right. So we found a general solution. But in order to finish the rest of it, right, because there's sort of like a part A and a part B, what we need to think about is how those other parts give us whatever initial conditions we need, okay? So in part A, oh, that's a good question. Hang on to that question for a little bit. Let's kind of finish what we're doing here and then we'll address that question, okay? I'm wondering if you can help me interpret, and this is you as a global you, the initial conditions here. So it says the mass is initially released from rest from a point 1 meter below equilibrium position, right? So we have initially released from rest from a point 1 meter below the equilibrium position. What does this tell us about our initial conditions? Good, good, good. Okay, so let's see. Initially released from rest. This means that initially the velocity is 0. Okay, so if we're practicing interpreting the initial conditions, we have that. And then this, where is it released from? The initial position was 1 meter in the same direction as gravity. So we're going to say it's a positive one. Okay. So then you would plug these numbers into your general solution. You would have to take that derivative, and when you take that derivative, you're going to need to use chain rule, but you should be able to apply the initial conditions and find a value for that. Okay. Let's take a look at the second set of initial conditions, like a different scenario, right? How does that change? And so the second prompt says that it is initially released from a point 1 meter below the equilibrium point with upward velocity of 11 meters per second. And so does that change my green initial condition? My x of 0 equals 1. Does that one change in the second scenario? No, you are correct. All right, so this 1 meter below still means that x of 0 equals 1, right? So that part stays the same. But the upward velocity part, right? So now we have an upward velocity of 11 meters per second. That is going to change my other initial condition. In fact, it's going to be x prime of 0 equals upward is opposite gravity, so negative 11. Okay. Was that helpful in terms of moving forward a little bit more in this problem? Okay, good, good. And for folks who said they had a little bit of trouble setting up examples 2 and 3, are we feeling a little bit more confident on that right now? And I know I heard a yes earlier from some people, but all right, good, good, good. Yes, I'm going to post the video from today, and I'll also post these notes, and I will not disappear and post them at like 5 p.m. I'll do them like right after class. Okay. All right.
Jude,
Yes, what's up?
if it was to say a downwards velocity, it would be a positive 11, right?
Because it would be in the same direction as gravity.
Okay.
All right. So the last question I think we'll have time to chat over is this idea on the different cases. So we're not doing that many higher level questions here. And so sort of makes it a little bit tricky, because when we're thinking about why some of these fancier forms, like why do we need omega squared when we could just write k over m? Like, why would we even do that? I'm trying to find a good example of when that might sort of pop up in your future experiences. Okay, so let me see. Okay, so I'm going to show you an example of when you might need to use some of the other notation. I'm going to stop sharing the screen for a moment. I'm going to share a different screen. Okay, so can you folks see that new screen? Yeah,
we got
okay. All right. So questions that might be common in a higher level differential equations class might look something like this. There's literally like no numbers, right? So when you're solving some of these differential equations, you're trying to work through the process as if everything was like a generic function. And so because there's generic functions, sometimes it's easier to say, all right, I have a lambda here, that's going to be some number, but I don't know exactly what it is. And so maybe more precisely to your question would be something like this. Okay, so this question, it's a heat equation that is like a really big deal in partial differential equations. You have to take a look at some initial conditions and some boundary conditions. But as you're deriving this, you might notice like I have like an alpha over k. Let me see if I can annotate. You might notice that I could see like an alpha over k here. And so why would I maybe want to write it as alpha over k? In this case, I did, but when I was solving this characteristic equation, I was able to say lambda squared equals that, and I was getting a value for lambda. And the nice thing about that is that later on, when I'm trying to, that's not working. Later on, when I'm trying to find a value, it's nice to have something as like a lambda squared, because then you'll sub back in a lambda instead of this weird square rooty looking thing. So for example, what might be, okay, so one of the things that you'll see a lot is something like, oh, the square root of lambda is this n pi over L, but I don't really want to write square root of lambda. So instead of doing that, we define it as n pi over L. So we avoid the idea of a square root, and it just makes a lot of the other computations a little bit easier. All right, so that's sort of a I don't know, perhaps a not very satisfying answer to your question. But when you're thinking about like, why do we have these different versions when we can sort of get away with more simple cases right now? The answer is we can get away with those simple cases right now, but we're also creating familiarity and structure for future classes to come. Okay. So I think this might be a good time to kind of wrap things up. I hope today's session was helpful. Everyone posting in that discussion was definitely really helpful for me to think about what we might do. And I'll go ahead and post the video and notes for this as soon as we're done.